All right, welcome back, everybody. So we're going to start working on some examples for the mean value theorem. So for number 2, we want to determine if the mean value theorem applies to the following functions. So, and then if it does, find all values that satisfy the conclusion. So let's just note here, we've got f of x equals 3x squared plus 2x plus 5. So f is a polynomial, which means it is continuous and differentiable everywhere. So it's definitely continuous on -1, 1, differentiable on the open set -1, 1. Okay. So MVT definitely applies. So let's note what f of b minus f of a is going to be. So f of 1 minus f of -1 all over 1 minus -1 is going to equal our f prime of c value. So f of 1 is going to be 10 minus f of -1 is going to be 8 minus 2, which is 6, and then 1 minus -1 is 2. So we're going to get f prime of c is equal to 4 over 2, which is 2. So there's going to be some point on this slope, at least one, where the derivative is equal to 2. So let's go ahead and find that value. So we'll just note that f prime of x is equal to 6x plus 2, and it equals 2 somewhere on this interval. So 6x equals 0 then, x equals 0. So the slope is equal to 2 at 0. And clearly we can see that 0 is inside of our little subinterval here, our closed subinterval. So we are done. So x equals 0. All right, so -8 to 8 of x to the 2/3. So no matter what value of x we get, this is going to again be the cube root of x squared, which is going to exist everywhere on those. So we'll note the MVT applies. On -8, 8, because we don't have any discontinuities to worry about, or cusps to worry about. Oh, wait. Oh, no. I spoke too soon. So this is definitely continuous, but is this differentiable everywhere? So yeah, we do need to make a note here. F prime of x is equal to 2/3 x to the -1/3. And note f prime of 0 does not exist. We're going to have an infinite discontinuity. So the MVT does not apply. So be careful. It's not just continuity, but it's also going to be its differentiability. Okay. All right, so we'll look at C here. So again, we'll need to be slightly careful with our differentiability rules here. So f prime of x is going to be 1/2, 2 minus x to the -1/2 times -1. Which is going to equal -1 over 2 rad 2 minus x. So for this, we're going to have an issue at 2, obviously. But 2 is an endpoint. So that's okay, because we only need to be differentiable on the open interval, not the closed interval. So note f is continuous on -7, 2. And differentiable on the open interval. So thus MVT applies. All right, so let's go ahead and figure out what our average rate of change is here. So we'll have f of 2 minus f of negative 7 all over 2 minus negative 7. So f of 2 is going to be 0, minus f of negative 7 is going to be 2 plus 7, which is 9. So the square root of 9 is 3, all over 2 minus negative 7, which is 9. So it looks like we're going to get negative 1/3. Okay, so we want to find all values such that our slope is equal to negative 1/3. So let's go ahead and move that over. So we've got negative 1 over 2 rad, 2 minus x is equal to negative 1 over 3. And now we can focus on this one. So we can cross multiply here and then cancel the negative signs, since clearly we can divide by negative 1. So we'll get 3 is equal to 2 rad 2 minus x. We can square both sides. Oh, whoops. Let's divide by 2 first. So 3 over 2 is equal to rad 2 minus x. And then we'll square. So we'll get that 9 over 4 is equal to 2 minus x. So we'll get that 9 over 4 minus 2 is equal to the opposite of x. So that's 1/4, which means x is equal to 1/4. Sorry, negative 1/4. So at x equals negative 1/4, we will have a slope of negative 1/3. All right, so again, be sure to check both continuity and differentiability for those algebra examples. Let's go ahead and move on here. So we've got a couple of different examples here as well that are going to be more kind of analytical, where we're not given a explicit function. So f is continuous and differentiable on negative 3, 3. Suppose that f of 0 is negative 3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? And so for this one, we know that we can consider, well, okay, so let's look at, so we know that f prime of c is going to equal f of 2 minus f of 0 all over 2 minus 0. So that's going to be true on our subinterval 0 to 2, which is inside negative 3 to 3. But we want to know how large can f of 2 possibly be. So if we want it to be larger, we want it to be increasing. So we're going to choose f prime of c to be the biggest possible value. So we'll let f prime of c equal 5, and then we'll go ahead and solve. So we've got 5 is equal to f of 2 minus f of 0 is negative 3, so that'll be plus 3, all over 2. So we'll get 10 is equal to f of 2 plus 3, so 7 is equal to f of 2. And this is really the same as just assuming the slope is 5 and then adding 5 for each value between. So no, we didn't really need to use the mean value theorem here, but this is a question that does come up from time to time. So you could justify it using the MBT or just an inequality argument. So number 4, does there exist a function such that f of 0 is negative 1, f of 2 is 4, and f prime of x is less than or equal to 2 for all x? So again, same question, which is, given 2 points, can this value exist? So let's look at, f of 2 minus f of 0 all over 2 minus 0. So if that's our slope between, right, let's see what we get. So we're going to get 4 plus 1 over 2 is equal to 5 halves. So if this function existed, and we'll assume it's continuous and differentiable, then this statement could not be true, right? Because f prime of c would have to equal 5 halves somewhere on the interval 0, 2. Right? So the only way that this could exist is if this function was not continuous or not differentiable. We'd have to have some sort of an issue there. So by the MBT, this is not true. And then finally, we'll look at another fun example. So when you are driving on a toll road, what typically will happen on the toll roads now, it's a little bit more sophisticated, but there will be a location where it takes a photo of your car entering the toll road, and then they will take a picture of your car exiting the toll road. And they will have the exact time that you were on the toll road there so that they can charge you. Nowadays, you know, you buy a pass and you don't pay a specific fee, you pay a regular fee. But we can actually use the mean value theorem to prove that somebody was speeding on that interval. So the speedometer of an automobile registers 50 miles per hour as it passes a mileage marker. 4 minutes later, as the car passes mileage marker 5 miles from the first, the speedometer registers 55 miles per hour. So can we prove that the driver exceeded 65 miles per hour? So we'll need to make an assumption here. So we're going to assume that the velocity of the car is continuous and differentiable everywhere, right? So at any given point, our velocity is changing in a continuous way, either increasing or decreasing. So we know that the mean value theorem is going to apply. From t equals 0 minutes to t equals 4 minutes. So we'll use this subinterval since it's given that 4 minutes later, we've got our second measurement. So on our specific measurement that we found from 0 to 4, where 0 is when we entered or passed the first mileage marker that we were at, and then 5 miles later. So we know that the average then, if we're looking at distance over time, so no, velocity is distance over time. So then our average rate of change is going to be 5 miles minus 0 miles. So we traveled 5 miles total, divided by 4 minutes. Okay, so that means that our average was 5 miles over 4 minutes, but we need to convert to miles per hour, obviously. So we can just multiply 60 minutes times 1 hour. So 4 will divide evenly into 60 as 15. And what we end up with is 75 miles per hour. So by the mean value theorem, since our velocity is continuous and differentiable in those 4 minutes, there must be a time C on our interval such that V of C is equal to 75 miles per hour. And because of that, we can mail you a ticket in the mail. and make you pay it. All right, so that's going to conclude our notes for Rolle's theorem and the mean value theorem. Again, this is going to be a very important standard for the AP course, so we're going to be dealing with it all the time. So make sure that as you're working on those homework examples, that you're being careful with how you're describing your work, as well as being careful with your algebra as you work through problems. So if you have questions, definitely shoot me an email. Otherwise, come by my office.